All right, welcome back. In this lecture, we continue looking at examples of the use of characteristic roots and characteristic vectors to calculate functions and determine properties of the square symmetric matrix from which they were calculated. In this lecture, we'll be looking at example 1.3. So let's take a look. So let cap sigma be the 2 by 2 matrix given here, with entries 4 and 1 in the first row and 1 and 2 in the second row. So this is a square matrix, and it's also symmetric. The question is it a valid covariance matrix? And to answer that question, we have to determine whether it is non-negative or not. And so to answer that question, we'll need to find lambda 1 and lambda 2, the characteristic roots of cap sigma. Once we've done that, we'll find the general form of the characteristic vectors of cap sigma corresponding to each of the characteristic roots lambda 1 and lambda 2. We'll then verify that C1 and C2, which are arbitrary characteristic vectors of cap sigma corresponding to its characteristic roots lambda 1 and lambda 2 respectively, are orthogonal, and we'll do this by showing that their inner product, C1 prime times C2, is equal to 0. Then, from C1 and C2, we'll find length 1 characteristic vectors of cap sigma corresponding to lambda 1 and lambda 2. We'll then verify that the trace of this matrix is equal to the sum of its characteristic roots. We'll also verify that the determinant of this matrix is equal to the product of its characteristic roots. We'll then answer the questions: is cap sigma positive definite? Is it positive semi-definite? And then, is it non-negative? Once we've answered those questions, we'll be able to answer the question, is cap sigma a valid covariance matrix? And then finally, we'll answer the question, could cap sigma be the covariance matrix of a multivariate normal distribution? If so, we'll define a 2 by 1 random vector x to have a multivariate normal distribution with covariance matrix equal to this particular sigma, and we'll answer the following questions. We'll find the variance of x1, the variance of x2, we'll calculate the correlation of x1 and x2, and then we'll answer the question, does a PDF exist for this distribution? So let's take a look at the solution for this set of problems. So the characteristic polynomial of cap sigma is equal to the determinant of the matrix cap sigma minus lambda times the identity matrix, and the characteristic equation is obtained by setting that characteristic polynomial equal to 0. Now the determinant of this difference between cap sigma and lambda times the identity matrix is equal to, as you can see here, the determinant of the 2 by 2 matrix with entries 4 minus lambda and 1 in the first row, and then 1 and 2 minus lambda in the second row. Now again, recall that the determinant of a 2 by 2 matrix is equal to the product of the diagonal elements minus the product of the off-diagonal elements. So in the notation that I've got here in red, it would be the product of A and D, the diagonal entries, minus the product of C and B, the off-diagonal entries. And so the determinant of the matrix we have here would be equal to 4 times lambda times the quantity 2 minus lambda, and then from that we would subtract 1 squared. And when you expand 4 minus lambda times 2 minus lambda and then subtract 1, we get lambda squared minus 6 times lambda plus 7. Now we can solve this equation using the quadratic formula, which gives solutions to the equation as equal to lambda equal to 3 minus square root of 2 and 3 plus square root of 2. And so the characteristic roots of cap sigma are therefore lambda 1 equal to 3 plus the square root of 2, and the second characteristic root, lambda 2, equal to 3 minus the square root of 2. All right, next we're going to find the characteristic vectors of cap sigma. And so to do this, let lambda be an arbitrary characteristic root of cap sigma. Then, by definition, the following equation has to hold. So cap sigma times the 2 by 1 non-zero vector c must be equal to the product of this lambda, this arbitrary characteristic root of cap sigma, times the 2 by 1 vector c, where c is some non-zero vector, and we'll denote the entries in the 2 by 1 vector by c1 and c2. Now, when we carry out the matrix multiplication, we see that this equation, this matrix equation, implies that c1 and c2 must satisfy the system of two equations given here. So 4 times c1 plus c2 must be equal to lambda times c1, and c1 plus 2 times c2 must be equal to lambda times c2. Now, subtracting lambda times c1 from both sides of the first equation and lambda times c2 from both sides of the second equation results in the following equivalent system. So the first equation would be 4 minus lambda times c1 plus c2 equal to 0. And then in the second equation, we have c1 plus, and then the quantity 2 minus lambda times c2, and that must be equal to 0 as well. Now, for a given characteristic root, lambda, c1 and c2 must satisfy this system with at least one of those two constants, c1 and c2, being non-zero. So let's find the general form of characteristic vectors of cap sigma corresponding to the first characteristic root, 3 plus the square root of 2. And so plugging that value, 3 plus the square root of 2, in for lambda in the two equations on the previous slide, we get the following system. So the first equation is the quantity 1 minus the square root of 2 times c1 plus c2 must be equal to 0. And the second equation is c1 minus the quantity 1 plus the square root of 2 times c2 equal to 0 as well. Now, if we multiply the first equation by 1 over 1 minus the square root of 2 and subtract that from equation 2, we get the following single equation. That being c1 equal to negative 1 over 1 minus the square root of 2 times c2. So we have a single equation with two unknowns, and that implies that there are an infinite number of non-zero c vectors that satisfy this equation. Okay, that implies that there are an infinite number of characteristic vectors, bold c1, of the matrix cap sigma corresponding to the characteristic root lambda 1 equal to 3 plus the square root of 2. So let c2 be equal to t, an arbitrary non-zero real number. Then any vector c1 of the form bold c1 equal to And you can see here the 2 by 1 vector. We have two representations of it. The first is -1 over 1 minus the square root of 2 in the first row and 1 in the second row. And then multiplying that 2 by 1 vector by t, this arbitrary non-zero constant. The second representation being -t over 1 minus the square root of 2 in the first row and t in the second row. So any vector of that form is a characteristic vector of cap sigma corresponding to the first characteristic root, lambda 1, equal to 3 plus the square root of 2. So that is the general form for the characteristic vectors of cap sigma corresponding to the first characteristic root of cap sigma. All right, now let's find length 1 characteristic vectors of cap sigma corresponding to the first characteristic root. We first note that the squared length of C1, which is given by C1 prime times C1, the inner product of C1 with itself, that gives the squared length of C1, which is equal to the quantity shown on the right-hand side of this equation. So the ratio, 4 minus 2 times the square root of 2 over 3 minus 2 times the square root of 2, that times t squared. Now, in order for the vector C1 to have length 1, it must therefore be that this constant t must be equal to either negative the square root of 3 minus 2 times the square root of 2 over 4 minus 2 times the square root of 2, or the positive value of that. And so plugging in those values for t into the general form of the characteristic vectors of cap sigma corresponding to the first characteristic root, we get the length 1 characteristic vectors of cap sigma corresponding to the first characteristic root shown here. And we're going to denote those by A1 and negative A1. And I have here A1, and you can see here that it's a fairly complex 2 by 1 vector in terms of the quantities that make up the components. We have several square roots and fractions and so forth. But if we evaluate those, we can see that the length 1 characteristic vector of cap sigma corresponding to the first characteristic root that we're labeling A1 is approximately equal to 0.9239 in the first entry, or the first row, and 0.3827 in the second row. To get the other length 1 characteristic vector of cap sigma corresponding to lambda 1, we multiply that vector by negative 1, and so then both of those entries in the 2 by 1 vector would be negative. And so those two vectors, A1 and negative A1, they're both length 1, so they have the same length, and the only difference between them is that they're pointing in exactly opposite directions. Okay. Again, remember that the system of equations that a characteristic vector of cap sigma corresponding to characteristic root lambda must satisfy is given by this system of equations here. And so what we're going to do next is find the general form of characteristic vectors of cap sigma corresponding to its characteristic root lambda 2, which is equal to 3 minus the square root of 2. So plugging 3 minus the square root of 2 in for lambda in the system of equations on the previous slide, we get the following system of two equations. So the quantity 1 plus the square root of 2 times C1 plus C2 equal to 0. The second equation is C1 minus, and then the quantity 1 minus the square root of 2, that times C2 equal to 0 as well. Now, if we multiply the first equation by 1 over the quantity 1 plus the square root of 2, and then subtract the result from equation 2, we get the following single equation: C1 equal to negative 1 over the quantity 1 plus the square root of 2 times C2. And as before, we have a single equation with two unknowns. Because of that, we know that there are an infinite number of non-zero C vectors that satisfy this equation. This implies then that there are an infinite number of characteristic vectors C2 of the matrix cap sigma corresponding to the characteristic root lambda 2 equal to 3 minus the square root of 2. Okay, so let's let C2 be equal to t, an arbitrary non-zero real number. It then follows that any vector C2 of the following form, so the 2 by 1 vector with negative t over 1 plus the square root of 2 in the first entry in the first row, and t in the entry in the second row, any vector C2 of this form is a characteristic vector of cap sigma corresponding to the characteristic root lambda 2 equal to 3 minus the square root of 2. All right, now let's find length 1 characteristic vectors of cap sigma corresponding to this second characteristic root. To do that, we first note that the squared length of C2, which is equal to the inner product of C2 with itself, C2 prime times C2, that is equal to the expression on the far right-hand side. So the ratio 4 plus 2 times the square root of 2 all over 3 plus 2 times the square root of 2, that ratio times t squared. And so if we set that equal to 1, all right, and then solve for t, we see that t must be minus or plus the negative or the positive value of the square root of 3 plus 2 times the square root of 2 over 4 plus 2 times the square root of 2. And if t is either of those two values, that will result in a length 1 characteristic vector of cap sigma corresponding to its second characteristic root. And so plugging the positive value in for t into the general form for the characteristic vector, we get the length 1 characteristic vector of cap sigma corresponding to lambda 2. And so you can see here that that vector, which we're denoting by A2, has entries negative 0.3827 approximately in the first row and positive 0.9239 in the second row. Now, the other length 1 characteristic vector of cap sigma corresponding to its second characteristic root would just be the negative of that vector. And so in that vector, the entry in the first row would be positive and the entry in the second row would be negative. All right, so A2 and negative A2 are both length 1 characteristic vectors of cap sigma corresponding to the characteristic root lambda 2, and they're pointing in the exact opposite directions from each other. Okay, next we're going to verify that the characteristic vectors of cap sigma corresponding to different characteristic roots are orthogonal. And the way we're going to do that is to show that C1 and C2 have an inner product that is 0. In other words, C1 prime times C2 is equal to 0. And so C1 prime times C2 is equal to the expression here on the slide. And if you go through and do the calculations, and especially if you focus on the next to last expression on the right-hand side, you see that that evaluates to 0. And so since C1 prime times C2 is equal to 0, this implies that the two vectors C1 and C2 are in fact orthogonal. Okay, next we're going to verify that the trace of cap sigma, which is the sum of its diagonal elements, is also equal to the sum of its characteristic roots. And so using the definition of the trace, again that being the sum of the diagonal entries, the diagonal entries in the matrix were 4 and 2, and so they add up to 6. The sum of the characteristic vectors is 3 plus the square root of 2 plus 3 minus the square root of 2. And so the positive square root of 2 and the negative square root of 2 cancel out, and so we're left with 6. And so we see that the trace of the matrix is equal to the sum of its characteristic roots. Next, we're going to verify that the determinant of cap sigma is equal to the product of its characteristic roots. Now again, the determinant of a 2 by 2 matrix is equal to the product of the diagonal entries minus the product of the off-diagonal entries. And so that would be 4 times 2 minus 1 times 1, 8 minus 1, which is 7. The product of the characteristic roots is 3 plus the square root of 2 times the quantity 3 minus the square root of 2. That turns out to be 9 minus 2, which is 7. And so again, the property is verified. And we can see here that and you can imagine that as we get up into higher dimensional matrices, that it's going to be much easier to calculate the determinant using this kind of a property than it would using the definition. All right, now we'll answer the following questions. Is cap sigma positive definite? Yes, it is. Since both characteristic roots of cap sigma are positive, cap sigma is positive definite. Is cap sigma positive semi-definite? No, it's not. Although both characteristic roots of cap sigma are non-negative, neither is equal to 0. Therefore, cap sigma is not positive semi-definite. Is cap sigma non-negative? Yes, it is. Because cap sigma is positive definite, it's non-negative. You'll recall that in order for a matrix to be non-negative, it has to be either positive definite or positive semi-definite. In this case, the matrix is positive definite, and so it is non-negative. Is cap sigma a valid covariance matrix? Yes, it is. Because cap sigma is a square, symmetric, non-negative matrix, it is a valid covariance matrix. Could cap sigma be the covariance matrix of a multivariate normal distribution? Yes, it could. Because cap sigma is a valid covariance matrix, it could be the covariance matrix for a multivariate normal distribution. All right, and so with that in mind, we'll define a 2 by 1 vector x to have a multivariate normal distribution with covariance matrix given by the cap sigma that we're using in this example. And so in that case, the variance of x1, the first random variable in the vector, the variance of x1 would be 4. The variance of x2 would be 2. The correlation of x1 and x2, you'll recall, is the covariance of x1 and x2 divided by the square root of the product of its variances. And so that is equal to 1 over the square root of 4 times 2, or 1 over the square root of 8, and that evaluates to approximately 0.3536. Does a PDF exist for this distribution? Yes, it does. Because cap sigma is positive definite, its inverse exists, and so the PDF will exist for that distribution as well. All right, so that wraps up this particular example. What I would encourage you to do in all of these examples that we're going through is to make sure that you can work them yourself. Go through each example, work them out by hand, use a calculator, use software, however you want to do the calculations. That will be fine. But just make sure that you're following along, that you understand the definitions, that you understand the various calculations, that you understand the use to which we're putting these various quantities, like the characteristic roots and so forth, right, in determining characteristics of these matrices. So just work through these examples on your own. Make sure that you can replicate what we've done here in the lecture. We'll look at some more examples in the next lecture video.